Welcome back to section 1.4, composition of functions. This is part 2. So we're still evaluating composite functions. We're going to evaluate them using a table. So what this gives you is your x values. These, notice, are the values of f of x for this x, and these are the values of g of x for this x. Right? Okay. So we need, first off, we're going to have to find these two. We're going to need f g of 3. That's going to equal f. And what's g of 3? So let's see. X is going to equal 3. Right here. And what does g of x equal? 2. Now we need f of 2. So what is, when x equals 2, because that's what this is here, x, it equals 8. Now what about g of f of 3? Well, f of 3, when x is 3, f is equal to 3. When x is 3, g of x is equal to 2. And that's how we would evaluate them using a table. So evaluating composite functions using graphs, that is very similar to a table, except you have to go and get the values yourself from the graph. So we're going to evaluate, it wants us to evaluate this one, but I'll go ahead and have you guys evaluate both of them. Okay, so first we're going to do this one. F of g of 1. So g of 1, we're going to go to the graph of g. We're going to go to x is equal to 1. And what is the graph when x is equal to 1? I'm going to say that's about 2.5. And these are estimates, which is okay, because sometimes no two people get the same answer. So now I need to find when x equals 2.5, so I need to find f of 2.5. So we go to f, we look up, let me erase all these. The screen is really sensitive. We're going to go to the graph of f, we're going to go where x is 2.5. So right here, we're going to go all the way up, and it's going to equal, we'll say about 6. That's good enough. So this equals about 6. So what about the second one? So when f equals 1, we go to the graph of f, we find 1, we go to where it intersects, I'm going to say it's about 2. And then we're going to use that to find g. So g of 2, we go to the graph of g, we find 2, and that equals 0. So this equals 0. Now we're going to be evaluating these functions using formulas. So for a, I have h of f of 2. So f of 2 is equal to, this is f, this is h. Anywhere where there is a t in f, we're going to put a 2. Oh, minus 2, almost put a t. So that's 4 minus 2 equals 2. So now we're going to just replace that here. So we need h of 2. And in h, everywhere you see an x, you now have a 2. And that's 8. So this whole thing equals 8. Now b, we need h of f of negative 2. So first we need f of negative 2, and we do it just like above, except we put negative 2 everywhere where t is. And then we use that for our x in the h, and everywhere we see an x, we put f of negative 2. So this whole expression equals 20. The whole equation, I suppose. Now, finding the domain of a composite function. So the domain is going to depend on f and g. So you are going to find the domain of g, or your inner function, and then you find the domain of f, or your outer function, and then you are going to find values of x where g of x is not in the domain of f. And you would exclude those. And we will have an example. Finding the domain of a composite function. Oh, one thing, if you guys ever want to know where we are in terms of the lecture and the video, this right up here says page blank of blank. So right now it says page 13 of 16. I know it's really small. I can't make it any bigger, but some people do like watching that for whatever reason. So I'm just going to point it out. So finding the domain of a composite function. So remember, first we're going to find the domain of the inner function. And remember, this guy is the inner function, that g, because f of g, that fog, is equivalent to this. So my g of x equals 4 over 3x minus 2. So one rule here, a rational function like this, is that you can't divide by 0. So I think we all know that the bottom can't be 0. So I'm going to find where it equals 0. And this x is not in my domain, and that's the only number that's not in my domain. So it goes from negative infinity to 2/3, unioned with 2/3 infinity. Now we're going to find where f of x does not have a value in the range. So what that means is, what value of x can we plug in and it just like goes haywire. Notice here it's rational again, so the x is on the bottom. We cannot divide by 0, so I'm going to find where it equals 0. So x cannot equal, just like up here, x cannot equal, here, let me get a little red going, cannot equal 2/3. Here, x cannot equal 1, because when it does equal 1, we get 1 minus 1 equals 0. When this equals 1, we get 3 times 2 over 3 minus 2 equals 2 minus 2 equals 0. See, that's a problem. So that means that f of x, f of whatever's on the inside, cannot equal 1. Since g is on the inside, we need to find, and this is because x equals g of x, right? Because it's the inner function from up here. So now we need to find where g of x is equal to this value 1. Since we need to exclude it, we're going to need to exclude any value of x that gives us a g of x of 1, if that makes sense. So if g of x cannot equal 1, then 3 of x minus 2 cannot equal 1. Oh, 4, because this is g of x. 4 divided by 3x minus 2 cannot equal 1. If we multiply by 3x minus 2 on both sides, we can just move it over. You may be tempted to multiply by 1/4 to get the 4 off of the top, but you're still going to have to multiply by the bottom, the denominator, in the end. So now we move the 2 over by adding it, and we divide by 3. So x, it looks like, cannot equal 2. So when x equals 2, that means g of x equals 1. So we'll go just a couple of steps here. So x cannot equal 2. If x were to equal 2, then that means that our g of x would equal 1. Right? Here, I guess I'll verify that. So 4 over 3 times 2 minus 2 is 4 over 4 equals 1. See, so g of x equals 1 when x equals 2. And then you take that g of x and you put it into f of x. So if we're going to put that f of x, that g of x into f of x, g of x equals 1. So if x equals 1, because g of x equals x, then we get 5 over 0, which can't happen. So this is the process that we're going through. You're finding the domain of g, which is this guy right here. Then you're finding the values of f that do not produce the values of your outer function. Doesn't have to be f. Your values of your outer function that are not valid. So the values in the domain that do not produce a good value in the range. So here it was x cannot equal 1. And then the next thing you do, so this now is our third step, is we are now going to exclude this x from this domain. So we're going to have negative infinity 2/3 unioned with 2/3 2 unioned with 2 infinity. And that's now the domain of f of g of x. Super long process, I know, I'm so sorry. If you know an easier way, run it by me, I'll listen. So now we're going to move on. So now we need to find the domain of f of g of x, where f of x is 1 over x minus 2, and g of x is the square root of x plus 4. So I'm going to find my domain of g of x. That's what I'm doing here. So I know that a square root function, the inside of it has got to be greater than or equal to 0. So x plus 4, I need that to be greater than or equal to 0. So x has to be greater than or equal to -4, which gives me -4, infinity. That's my domain of that. Now I have to find the values where f of x, the values of x where f of x does not exist. And since I have this, I know that this can't equal 0. Since this can't equal 0, x can't equal 2, right? Because x minus 2 equals 0, x equals 2, but we know it can't equal 0. So now we have to exclude that from this domain. So we get -4, 2, open bracket of parentheses because we're not including 2, unioned with 2, infinity. And remember, an infinity always has a parenthesis. Always. Okay, decomposing a composite function into its component functions. This one really is not too bad, I don't think, in my opinion. Once you see it, you'll be like, aha! So let's take this for an example. So if you were to have a composite function, you would plug in a function for everywhere that there's a variable in your equation. So suppose that f of x is actually equal to g of h of x, right? Perfect, we're getting that down. Where our inner function is h of x, and our outer function, we'll call that, we'll go ahead and call that g of x and be consistent with the book, since they like to use x for both of them. Traditionally, you would not use the same variable. Okay, so I need to find out what my two original equations are from this. And they have to include variables x, right? Because I've got it noted here. So let's say, so h of x is my inside function. So let's say if I make x squared be h of x, then I would get 5 minus h of x square root. Now, just looking at it, does that maybe look like you might be able to make it simpler? Just look at it. Just looking at it. Just look right at it. Does it look like it could be any simpler at all? Looks like it could be slightly simpler. Just, because there's so many pieces to it. If it doesn't look super simple here, it's probably not simplified enough. So that, I think we can do better. So let's say I want to make h of x now, I want to make it all of this. So then that gives me g of h of x is the square root of h of x. And that looks really simple, and that is actually correct. H of x equals 5 minus x squared, and g of x equals the square root of x. Now, a little hint here, if it is square root function or cubic function, more than likely the entire expression under the radical, that's called the radicand, will be your function. And then your other function will simplify to the square root of x. There's one more example here. Here we go for example. So let's say that f of x is equal to g of h of x. So h is our inner function, and g is our outer function. So if I were to make just x squared be h, then we would occur, like the same problem we had last time would occur. So I'm going to go ahead and immediately start out with trying to make 4 plus, and this is a guess, we're going to make h of x equal to 4 plus x squared. And then g of x is going to be equal to 4 divided by 3 minus the square root of h of x. Now that still kind of looks like it could get simpler, right? In my opinion, I'm just a teacher and all, but it does look like it could get simpler. So now I'm going to try and make h of x equal to everything underneath that fraction in the denominator. And then that gives me a g of x of 4 over h of x. Does that look pretty simple? That looks incredibly simple, which means that we would get 4 over x. And that's the one that I would go with personally. So what this means, to sum it up, h of x is equal to 3 minus the square root of 4 plus x squared, and g of x is equal to 4 over x. And then when we combine them into g of h of x, we get f of x. Well, that about sums up 1.4. I will see you in the next one.